Good morning or good afternoon or whichever it is, maybe even good evening for you. We've got today's notes on concentration versus time. And I am right now really wishing that my den where I'm videoing this wasn't like 5 feet wide and I didn't have to do this to talk to you. But there's more Easter bunnies behind me and I am out of room, so I'm doing the best I can with this board. I hope you can read, and if not, you can pause, zoom in, whatever makes you happy. There were a lot of weird notes today, going from differential to integrated rate laws, which would be a calculus lesson that I hope you had. Differentiation and integration. I'm not going through the calculus. If you would like to see the calculus, you can Google, or you can ask and I can Google. But I'm going to focus on what the integrated laws are. It's important for you to be able to tell the difference among what you'll see for first, second, and zero order. We are not going to talk about third. The graphs of these reactions will be very different and something you'll be doing a decent amount in here. So starting off, and I'm going to stand up and leave you to the giant dented whiteboard. Eventually I'll move it so you can see zero order also. For my first order reactions, you do have your differentiated rate law in your differential law in your packet, but the integrated rate law for these has natural logs in it, ln. Big boy calculators know ln just fine. What we're concerned with rate laws is concentration originally and concentration at a given time. For this one, for first order, so, okay, just A, not squared, I'm getting to my natural log of concentration of AT over AO. AT is my concentration at a specified time, which would be this time, and my A0 would be my original concentration. So what I'm looking for here, and it makes sense with rate, is how much a concentration is changing in a given amount of time. From last lecture, K is your rate constant. It's going to be reaction and temperature specific. I wrote out this format down here. Remember, if you have natural log of something over something, it's the same as subtracting the first natural log minus the second natural log. That's where I got that form from, the second one. The pink isn't the best to see, but it should work. My top one is the one you'll use more often, and the one I set up in the example. The first order reaction has a rate constant in hours. There you go, no big deal. Eventually you'll make that seconds. If the initial concentration is 1.25 times 10 to the negative third, how many seconds, so I'm looking for time, does it take to drop? ln of my concentration at T, so that would be the 0.31, it's on top, and 1.25 at the bottom. So we've got those, and then dividing by my rate constant to get T by itself, giving me 8.2 hours, or 2.9 times 10 to the fourth seconds. Nothing that exciting. So for your first order reactions, always check your problem, which reaction type it'll be is in there. And we've got then lots of good stuff with first order. Basically, sub into that equation if you've got concentrations at two different times and are looking to solve for time, or looking to solve for what is the rate constant. You can also solve for one concentration given the other information. Second order works the same way. Only thing is, when you get to your integrated rate law with the AT and AO, hang on one second, it is good. I was just making sure I've written it correctly. Notice that there are no natural logs in here. The equation is 1 over my concentrations. It's similar, very similar otherwise, except for one thing. What you'll notice here, negative K, no negative K. We'll see that again with graphing, which I'll talk about in a couple minutes. So for my second order reaction, it's going to be the same thing. I've given you the slopes on those. I guess I've already mentioned that. When I graph them, my slope will be negative K here. My slope will be positive K here. We're going to see that second order is the odd one out, that zero order, if you graph zero order, I don't feel like I'm going to make you graph zero order. Zero order is like plain oatmeal. Boring as you can get. So for a zero order reaction, though, we've got the rate disappearance independent of my concentration of A. A doesn't appear in my equation at all, and My rate law is therefore boring also. Concentration of A at time t equals negative kT plus AO. So, again, negative K is the slope of my reaction, which would make sense because concentration doesn't matter. If you look on the next, or right below this, I put this in your notes for this, but it's not in the packet. It's going to have to get to the packet. I put in examples of the graphs of these things, and that's a big deal. The graphs of these are something we will use often. If you were to do one of these reactions, and I'm still looking for an online something for you to do, at least with the data, kinetics of a clock reaction, if you want to see it, it's iodine clock, and it works this way very well. It's an example of kinetics. It's the classic kinetics lab. We were going to do it. For these graphs, if you will look, we always put time on the x-axis. We put the A thing, the concentration thing, on the y-axis. We say that as concentration versus time. For a first order, actually we're going in order on yours, for a 0th order reaction, made up word, we've got concentration of A and time. So we're looking at the concentration with time. For first order, ln of A with time. So I'm graphing my change in concentration of A, but using natural log to get a straight line graph, which is going to give me negative K for the slope. And for second order, backward slope, graphing 1 over A versus time. Those are important. Those are in today's practice problems. So your graphs go this way, and that way when you do them. Half-life is cool because half-life is easy. Half-life is like what we do. Actually, let's just do this. Half-life is like what we do when we don't know what else to do for calculations. Half-life literally means how long it takes half of something to decompose. So if I start with 100 grams, how long does it take either through a reaction or just like poof going away like nuclear chem? How long does it take for half of it to be gone? So we're looking at, in this case, with a reactant, but it's going to work the same way. So your first half-life is how long it takes to get to 50% of the original. Second half-life, how long it takes to get to 25% of the original. And I put a chart in there. I did. That is what it is. That amount of reactant present, if I start with 1, after 1 half-life, will drop down to 5. Actually, I think I'm going to update that. I need to shift my numbers down showing the half-lives. You'll see what I mean. It should say 1 beside 0.5. It should say after 2 half-lives beside 0.25. I'll update that. It'll be in the notes updated. Sorry about that. Hang on. I will fix. Like I said, you guys are the first ones to be using these notes. So I can fix them easier now because as soon as I changed online, you got it. So half-life for first-order reactions is the problem I swear I did 7,000 times in college. I remember doing this between kinetics and nuclear decay a million times. All it is your half-life equals 0.693 over K. It's a natural log thing also. I believe it's the natural log of 2 because of half-life. If you memorize that 0.693 over K, you're good. That's going to give you, based on your half-life, how long it'll take for half the sample to react. If you were to need a second order decomposition reaction, it is different. What you'll notice is that a first order half-life calculation is not dependent on your reactant concentration, whereas your second order half-life calculation does depend on the concentration because you're doing K times the concentration of A at the bottom. So it's going to be concentration dependent, not just on your rate constant. So you got your first order reaction at the bottom. Because it's first order, I can use 0.693 over K to calculate my half-life. And the other ones I did logically. I wrote through how I did them, and I think I showed the math on the one also. If it's not on that one that I showed the math, it's in one of your practice problems. I have it written down how I did it. It's fine. Half-life is relatively easy if you know the equations. You just need to remember that it's how long it takes for half of a reactant to react, to be gone. I'm going to put up the answers. I think I already put up the answers for the previous day's problem, like always. I'll be putting up the previous day's problems the next day. Feel free to ask if you have any questions. Your big takeaway message today is the difference in the graphs and the difference in equations. What the equations we saw today let you do is calculate one of these variables. You can get your starting concentration. You can either calculate rate constant, the time it takes, or your new concentration at a given time, because what we looked at today is the relationship between concentration and time. Remember, K is your rate constant, same for a given equation at a given temperature. So we got K, we're kind of settled with K. We're looking at how the concentration of a reactant A changes with time. All your calculations are on that. Good luck.